Hello! This lecture will present grammars and parsing as the formal and computational methods for investigating and modeling the linguistic phenomena. Context-free grammars are studied in fields of theoretical computer science, compiler design, and linguistics. They used to describe programming languages, and parse the programs in compilers can be generated automatically from context-free grammars. Patterns in sequences of words can be understood with respect to the phrase structure and dependencies, and we can develop formal models of these structures using grammars and parsers. A key motivation is natural language understanding. How much more of the meaning of a text can we access when we can reliably recognize the linguistic structures it contains? Having read in a text, can a program understand it enough to be able to answer simple questions about what happened or who did what to whom? We need a way to deal with the ambiguity that natural language is famous for. We also need to be able to cope with the fact that there are an unlimited number of possible sentences. So our goal is to answer the following questions. How can we use a formal grammar to describe the structure of an unlimited set of sentences? How can we represent the structure of sentences using syntax trees? How do parsers analyze a sentence and automatically build a syntax tree? Even in the most traditional forms of grammar, syntax is meant to show something more than just linear order. It shows how words group together and relate to each other as heads and dependents. The dominant method used for doing this within the last years has been to place tree structures over sentences. Language has a complex recursive structure, and such tree-based models, unlike Markov models, allow us to capture this. N-gram models and HMM tagging only allow to process sentences linearly. However, even simple sentences require a nonlinear model that reflects the hierarchical structure of sentences rather than the linear order of words. Thus, context-free grammars are the most natural model for tree structures, and the algorithms for them are closely related to those for HMMs. Before defining a context-free grammar, let's recall the most frequent syntactic categories, their symbols and their meanings. So the symbol S refers to this sentence. For example, the man walked. And P is a noun phrase. For example, a dog. VP is the verb phrase. For example, saw a park. PP is a prepositional phrase. For example, with a telescope. Det or the is a determiner. For example, the. N is a noun. For example, dog. V stands for a verb, for example, walked, and P stands for the preposition, for example, in. Context-free grammars can generate context-free languages. They do this by taking a set of variables which are defined recursively in terms of one another by a set of production rules. Context-free grammars are named as such because any of the production rules in the grammar can be applied regardless of context. It does not depend on any other symbols that may or may not be around a given symbol that is having a rule applied to it. Context-free grammars are used in compilers, and in particular for parsing, taking a string-based program and figuring out what it means. Typically, context-free grammars are used to define the high-level structure of a programming language. Figuring out how a particular string was derived tell us about its structure and meaning. A context-free language is a language that can be generated by a context-free grammar. Some languages are context-free and some are not. For example, it seems plausible that English is a context-free language. On the other hand, some dialects of Swiss German are not context-free. Regular and context-free grammars differ in the types of rules they allow. Context-free grammars allow individual words and phrases in any order and allow sentences with any number of individual words and phrases. Regular grammars, on the other hand, allow only individual words along with a single phrase per sentence. The formal definition of a context-free grammar, CFG, is that it is a four-tuple G which consists of these four elements. Here, N is a finite set of non-terminal symbols. For example, NP is a non-terminal which stands for noun phrase. Then we have sigma, a finite set of terminal symbols, which are words. For example, the word cat is a terminal. Then we have this set R, which is a finite set of rules of this form that x goes to y1 up to yn, where x is a non-terminal symbol, n is integer value, which is greater or equal to 0, and these y's can be either non-terminals or terminals for I from 1 up to n. And the last, fourth element of the grammar is the S symbol, which is a non-terminal that is distinguished start symbol. Here is an example of a context-free grammar. The set of non-terminals N contains the following non-terminals. S is a special start symbol. NP is a noun phrase. VP, verb phrase. PP, prepositional phrase. DT, determiner. VI, intransitive verb. VT, transitive verb. NN stands for the noun. IN for a preposition. S is a special start symbol. A set of terminals contains a set of specific words. For example, here we have the following set of words: sleeps, saw, man, woman, dog, telescope, the, with, in. And finally, we have the following set of rules. So the left table shows the rules with non-terminals, and the right table shows the rules where each of the non-terminals goes to a terminal. So let's see some examples. So first, the left table shows these non-terminal rules. So for example, S goes to NP, noun phrase, and verb phrase. And then we further decompose by using the set of following rules to decompose noun phrase, for example, either to a determiner and a noun, or to another noun phrase and prepositional phrase. Then a verb phrase can be decomposed to intransitive verb, or for example to a transitive verb and another noun phrase, or to another verb phrase and prepositional phrase. And also at the end we can see the rule for the prepositional phrase, which goes to a preposition and a noun phrase. The right table shows the following rules. For example, intransitive verb goes to a particular terminal, sleeps, or saw. And here we can see that these nouns go to particular nouns. For example, man, woman, telescope, or dog. Then we can see that the determiner goes to the, and these particular prepositions go to with or in. Given a context-free grammar G, a leftmost derivation is a sequence of strings S1 up to Sn, where S1 is the first string in the sequence and it consists of a single element, the start symbol. And Sn is the last string in the sequence. It is made up of terminal symbols only, and it is an element from sigma star. So sigma star denotes the set of all possible strings made up of sequences from words taken from sigma. And the rest of the SIs, that is Si, where I goes from 2 up to n-1, is derived from the previous one, that is Si-1, by picking the leftmost non-terminal x from Si-1 and replacing it with some beta, where x goes to beta is a rule in R. A context-free grammar G will in general specify a set of possible leftmost derivations. The set of possible derivations may be either finite or an infinite set, and each derivation can be represented as a pos tree, as shown with this figure here. If you want to illustrate the process of extracting leftmost derivations, we start with the start symbol, which is the first string in our sequence. The next string in our sequence would be NP-VP. Our leftmost non-terminal now is NP, so we use a rule from our grammar to replace it with DT and N. So our next string in the sequence would be determiner, now, noun, and a verb phrase. The leftmost non-terminal now is DT, so we replace it with a particular word, which is D in this case, so our next string from the sequence would be the noun verb phrase. Next, using the rule for NN, we would get the word man. So our next string in the sequence would be the man and VP. And finally, we use a rule to replace VP with VI. Intransitive verb. So our next sequence in the string is the man, VI. And finally, we use a rule to replace VI with a particular word, in this case sleeps. So our final string in the sequence would be the man sleeps. Context-free grammar defines a set of possible derivations. A string S from the set sigma star is in the language defined by the context-free grammar if there is at least one derivation that yields S. Each string in the language generated by the context-free grammar may have more than one derivation, which leads to ambiguities. A parser processes input sentences according to the productions of a grammar and builds one or more constituent structures that conform to the grammar. A grammar is a declarative specification of well-formedness. It is actually just a string, not a program. A parser is a procedural interpretation of the grammar. It searches through the space of trees licensed by a grammar to find one that has the required sentence along its fringe. A parser permits a grammar to be evaluated against a collection of test sentences, helping linguists to discover mistakes in their grammatical analysis. A parser can serve as a model of psycholinguistic processing, helping to explain the difficulties that humans have with processing certain syntactic constructions. Many natural language applications involve parsing at some point. For example, we would expect the natural language questions submitted to a question answering system to undergo parsing as an initial step. Ambiguity is an astonishingly severe problem for natural languages. When researchers first started building reasonably large grammars for languages such as English, they were surprised to see that sentences often had a very large number of possible parse trees. It is not uncommon for a moderate-length sentence to have hundreds, thousands, or even tens of thousands of possible parses. Here we can see two parse trees for the sentence "The man saw the dog with a telescope." Let's compare these two parse trees so we can conclude why this is the ambiguity example. So on the left side of each tree, we can see the noun phrase "the man." This phrase is the same for both trees. They differ in verb phrase at the right of the tree. So the left side example, our left tree, has the transitive verb saw and then the noun phrase, which is the object of the sentence. So here, the dog with a telescope is the object of the sentence. So the man saw the dog with a telescope. The telescope belongs to dog, not to man. Then the right tree has the verb phrase saw the dog and the prepositional phrase with the telescope, which refers to the man. So the telescope of the right parse tree belongs to the man. The object of the sentence is the dog. The man saw the dog. And the instrument that he was using to watch the dog is the telescope. So the telescope here belongs to the man. Another ambiguity example refers to the sentence "The dog saw a man in the park." Let's compare these two past trees to detect the ambiguity issue. So the subject of the sentence is the dog, which is indicated with a noun phrase as shown at both past trees. And next we have a verb phrase to show that saw is a predicate, a verb of the sentence, and a man is the object. So it is indicated with this verb and noun phrase as shown at both trees. So we also here have this verb saw and this noun phrase a man. However, the difference is in this propositional phrase, the adverbial of the sentence. So in the park, at the left side tree refers to the dog. The dog is the one who is definitely in the park, and he saw a man probably there, so the man might have also been in the park, but does not have to be necessarily. Probably he was there because the dog saw him, but the dog is one who was definitely in the park. And the right past tree uses this propositional phrase referring to the object of the sentence, which is a man. So the man is the one who was in the park, not the dog necessarily. The dog might have been in the park to see the man, but the dog did not had to be there. He might have seen a man through a window or from another planet using a telescope or wherever. He might have even been in the park, but he did not have to be there to saw the man. The man is the one who was definitely in the park. Another ambiguity example refers to the sentence, I shot an elephant in my pajamas. There are two past trees, so let's see the possible interpretations of this sentence. The subject of the sentence is I. The predicate of the sentence is shot, and the object of the sentence is an elephant. And the question is, how will we interpret this propositional phrase, this adverbial, in my pajamas? So if we look first at the left side tree, we can notice that in my pajamas refers to the subject of the sentence according to the structure of this tree. So I was in my pajamas while I shot an elephant. And then if we compare it with this right tree, we can notice that according to the structure of this noun phrase, which consists of a determiner, a noun, and a propositional phrase, we can conclude that this propositional phrase refers to the elephant. So the elephant was in my pajamas while I shot him. So we can notice the difference between these two interpretations. Also, I can see here that there is a slight mistake. My is not a determiner, rather it is a pronoun. Let's try to solve our first task and question 1a. So consider context-free grammar with the following rules, as shown here. Here, assume that S is the start symbol. So the question is, how many past trees are there under this grammar for the sentence? The man saw the dog in the park. The answer to our question 1a is that there is only one past tree for the sentence the man saw the dog in the park under the grammar and the specified rules. Here, the noun phrase can be decomposed either to a determiner and a noun, or to another noun phrase and a propositional phrase. There is only one rule for the verb phrase, this one here. So the verb phrase goes to the verb and a noun phrase, so there is no ambiguities here. We cannot show another past tree for this sentence under this grammar. So the object of this sentence is the dog in the park. So the man saw the dog who is in the park. The dog is in the park, not necessarily the man. The man can be also in the park, but does not have to be according to the structure of this sentence. The man, for example, might have seen this dog with the telescope from another location. Another question, question 1b, which refers to the same grammar from the previous question, where we assume that S is the start symbol, is how many apostrophes are there under this grammar for the sentence, "The man saw the dog in the park with the cat"? According to the specified grammar, we have two possible apostrophes. So let's see the interpretation of the sentence for apostrophe 1. Here, the subject of the sentence is the man. The predicate is saw. The object of the sentence is the dog. And the rest is this propositional phrase, "in the park with the cat." So, as constructed with this apostrophe, we can notice that this is an adverbial, which specifies the place where the dog was, where the man saw the dog. So we can say that this is the park with the cat. So the feature of this park is that it has a cat. It does not necessarily mean for this sentence that the dog is with this cat, or that dog sees this cat, or that anyone sees this cat, but it is important that this is the park where the cat is. So that is the interpretation of the sentence. The man saw the dog in the park where there is a cat. And this is the second apostrophe for the same sentence, so we can see how we can interpret the meaning of the sentence according to this tree. So again, the subject is the man, saw is predicate, and now the object of the sentence is the dog in the park. The dog is the object, the dog is in the park, and the dog has a company. He's with the cat. Now we can see that these two propositional phrases are now separated. So in the park is separated from this another proposition phrase, with the cat. So with the cat now does not refer to the park, but to the dog. So this cat is probably a company of this dog. So the interpretation of this sentence is that the man saw the dog in the park, the dog was in the park, and the dog was with the cat. So this cat does not necessarily live in this park. It is no longer the feature of this park as was in previous parts tree, but what is important is that this dog was with the cat. Let's move on to the question 1c. Define Cn to be the nth Catalan number. This is defined as the 2n factorial over n plus 1 factorial times n factorial. You can refer to the Wikipedia for a full description. It can be shown that Cn is the number of binary branching trees with n plus 1 leaves. Now consider a sentence that is grammatical under the above context-free grammar and has exactly k prepositions following the verb and 0 prepositions before the verb. A preposition is any word with the tag in. So the question is, how many apostrophes will this sentence have? And the answer is, k prepositions after the verb leads to a noun phrase after the verb that is equivalent to a binary branching tree with k plus 1 leaves. So we have ck apostrophes. So we obtain this number just by replacing n with k. So the answer is 2k factorial over k plus 1 factorial times k factorial. The grammar shown here at the right of this slide has the problem that it generates ungrammatical strings, such as the dog see the cat, the dog in the park see the cat, the dog in the park see the cat in the park, the dog sees the cat, the dogs in the park sees the cat, the dogs in the park sees the cat in the park. How would you modify the grammar so that all of the sentences that it generates are grammatical? Let's give a little hint. The new grammar should contain the following rules, which distinguish between singular and plural noun phrases. In order to solve this problem, we add a singular-plural distinction to the grammar. So we can see first that instead of just having noun phrase and verb phrase, we now have the rule noun phrase singular, verb phrase singular, and also noun phrase plural, verb phrase plural. And we accordingly adjust the rest of the rules. So now we have noun phrases for singular and plural for the rule determiner and a noun. And also, we distinguish between these two rules that include noun phrase and prepositional phrase. We also adjust accordingly the verbs according to the singular or plural, and we adjust the rest of the verb phrases accordingly. So now we can have for the verb phrase singular, we can have the base rule with noun phrase in either singular or plural, and then for the verb phrase in plural, we can have the verb with a noun phrase singular or plural. Also, for these rules with prepositional phrase, we also distinguish between singular and plural verb phrase. Notice that the rest of the rules remain the same.